Welcome to The Explainer. Today, we're going to break down the often intimidating math behind moisture in compressed air systems. Look, if you've ever dealt with pneumatic tools, factory piping, or just general manufacturing equipment, you know that water is the absolute enemy of a compressed air system. It causes rust, it ruins paint jobs, and it completely destroys expensive machinery. But actually figuring out exactly how much water is in your system and how to get it out, well, that can feel like a really complex physics exam. So today, we're going to make those calculations incredibly simple. Okay, let's dive into this by asking you to imagine exactly how much liquid water might be flooding your factory pipes every single day. And I'm not talking about a few drops here and there, I'm literally talking about buckets of water. You can't see it when the air is just floating around the room, but the moment you compress it, the physics completely change. We're going to look strictly at the numbers today to show you just how much water is hiding right in plain sight. Here is our agenda for today. 1. The invisible moisture problem. 2. The squeeze, compression math. 3. A real system example. 4. The air dryer difference. And 5. Best practices for dry air. Section 1. The invisible moisture problem. So before doing any math, we have to define our baseline capacity, which in this case is a standard 45 kilowatt compressor. Now, this size is incredibly common in medium-sized manufacturing. Our free air delivery, or FAD, which is really just the actual volume of air the compressor breathes in and delivers, is 7 cubic meters per minute. And we're going to place this compressor in a very average environment, a mild 20 degrees Celsius day with 50% relative humidity. Nothing extreme, just a standard Tuesday on the factory floor. And this brilliantly illustrates the core problem, right? Air behaves remarkably like a sponge, and its temperature totally dictates how big that sponge is. As temperature rises, the air's capacity to hold water vapor just skyrockets. At a chilly 4 degrees Celsius, a cubic meter of air only holds about 6.25 grams of water. At our baseline of 20 degrees, it holds 17 grams. But when things get hot, say up to 40 degrees, that exact same cubic meter can hold a massive 51 grams. The warmer the air, the more invisible water it can carry. Section 2, the squeeze, compression math. Okay, so the crucial point here is the compression ratio. This is where the magic, and honestly, the trouble, happens. To get to a standard working pressure of 8 bar from normal atmospheric pressure, which is roughly 1 bar, our compression ratio is 8. What does this actually mean for us? It means we're taking a volume of air and literally crushing it down so it's 8 times smaller. When we compress air to 8 bar, we are essentially squeezing our sponge 8 times tighter. And what happens when you squeeze a damp sponge? The water has nowhere to go but out. Let's trace the exact math on a static example to make this crystal clear. Before compression, let's take 8 cubic meters of air. At 20 degrees and 50% humidity, that air is naturally holding 8.5 grams of water per cubic meter. Now the compressor kicks in. It takes those 8 cubic meters and violently squashes them down into just 1 cubic meter. Now, all that water vapor didn't magically disappear, right? We just forced 8 cubic meters worth of water, which is 68 grams total, into a tiny 1 cubic meter space. But remember our sponge rule from earlier. At 20 degrees, 1 cubic meter can physically only hold 17 grams of water vapor. So if we cram 68 grams into a space that only holds 17, the math is brutal. 68 minus 17 leaves us with 51 grams. That 51 grams instantly turns from an invisible vapor into actual, physical liquid water falling straight out of the air. Section 3, a real system example. Now, let's take that static math and scale it up to a full day of continuous use, because this is where the numbers get truly shocking. If we follow the flow of our 7 cubic meter per minute compressor over a full 24-hour day, step 1 is finding our total volume. 7 cubic meters a minute times 60 minutes times 24 hours means our system breathes in a massive 10,080 cubic meters of air every single day. Step 2, we multiply that massive volume by our ambient moisture content of 8.5 grams per cubic meter. And that brings us to this staggering number. Your compressor is inhaling 85.68 kilograms of water every single day. Because a kilogram of water is roughly equivalent to a liter, to put that into perspective, that is over 85 liters, or more than 22 gallons of water, entering your compressor every 24 hours. Just on a mild, perfectly average day. No way, right? But it's true. Section 4, the air dryer difference. The question is, where does all that water go? The sheer volume of damage you can do by skipping one piece of equipment is unbelievable. If you operate without an air dryer, your compressor's aftercooler will do some heavy lifting. It squeezes out about 21.42 liters of water. But that still leaves a massive 64.26 liters of liquid water dumping directly into your piping system daily. Imagine pouring over 64 liters of water into your expensive pneumatic machinery every single day. But compare that to a system equipped with a refrigerated dryer running at a 4 degrees Celsius dew point. That dryer aggressively chills the air, wringing out the remaining 56.39 liters. The result? 0 liters of liquid water forming in your daily operations.
Let's trace this flow across the whole system to see how it works in practice. First, ambient air enters at 20 degrees. As the compressor squeezes it, friction spikes the temperature all the way to 80 degrees Celsius, trapping all that moisture as a vapor. Next, it hits the aftercooler. The temperature drops to 40 degrees, the sponge shrinks, and over 21 liters of water are wrung out. Then it hits the absolutely crucial step, the air dryer. By dropping the temperature all the way down to a 4-degree dew point in the refrigerated dryer, we shrink that sponge to its absolute minimum size, squeezing out another 56 liters roughly. Finally, as that air flows out into your warm factory, it naturally heats back up to around 30 degrees. And because we removed almost all the moisture when it was cold, this warmer air now has a massive capacity to hold water, but barely any water left in it. We're sending safe, bone-dry air at a highly protective 21% relative humidity straight into your facility.
Section 5. Best Practices for Dry Air. To wrap up our explainer, let's translate these mathematical realities into actionable maintenance steps. Because dry air prevents corrosion and equipment damage, it's really not enough just to buy the equipment. You have to manage the water it extracts. Always ensure your aftercoolers and refrigerated dryers are actively maintained. Install automatic drains at all the low points in your system because, well, gravity will always pull any rogue liquid to the bottom. And most importantly, regularly inspect those drains. A clogged automatic drain is basically just as bad as not having one at all. It'll just back up and send that water downstream right into your tools. Keep your system clean, keep it leak-free, and always respect the sheer volume of water your equipment is fighting against. So I leave you with this thought to take back to your facility. Based on the math we just covered, and knowing that dozens of liters of water are trying to infiltrate your lines every single day, is your system properly drained, or are you operating a very expensive water pipe by mistake? Check those drains, respect the math, and keep your air dry. Thanks for joining me on this explainer, and keep on learning.